Welcome back to Recursive Engineering. Today problem is unique paths. There is a robot on an M cross N grid. Okay, a robot is given on this M cross N grid, and the robot is initially located at top left corner. Okay, the robot tries to move to the bottom right corner. The robot can only move either down or right at any point in time. Okay, we have to reach this last row and column, and it can only move in this right or this bottom direction. And given these two integer mn, okay, the length is given, this grid length is given, and this mn, and we have to return the total possible unique paths so that robot can reach to this finish line. Okay, let's try to understand this. Let's take a table. Let's take a small example. Let's take a 3 cross 3 size grid, and suppose the robot is here and we have to reach this finish line, and I can only move in this right or this bottom. Let's take one way which I can reach. Suppose in this way I can reach to this finish, or in another way I can reach in this way. Let's try to take yes, in this way I can reach, or maybe I could take this way. And or I can, let's take this way. Or I can, is there any missing path here? Oh yes, I can take this way. So I am only moving in the right and the bottom direction, and I am reaching this finish line. This and if you count 2, 3, 4, 5, 6, and we have total paths of 6. And after looking at this problem, I can think of a recursive way, because I know there is two choices I have. I can take right or I can take bottom. What I will do, I will recursively call this right and this bottom and calculate all the paths, and after that I have to return that all the possible paths. And what is my base condition? I will check that if my I will take coordinate, let's say x and y in the start, and I will move this according to this right and bottom. And if my this x and y reach this last row and column, this last row, and this y reach to this column, I will say there is one way. Let's write the code. Let's say I have a function total paths. I will pass argument mn, and in the starting I have x and y 0. At the end I have to return this function. Done. Let's define our function here. I have a return type int because I have to return the total paths, and let's write our parameter. This is my x and this is my y. What I will do, I will say like if I have to discuss boundary case. Suppose if my x goes beyond this, I will say there is no way, please return 0. And if my y goes um, along this way, please return 0. So there is no possible path. So this is my boundary case. Let's write that if my x is greater than this, greater than and equal to this m, please, or this y greater than or equal to this n, please return 0. And if my x reaches the last row and y reaches the last column, please return 1. And I have to recursively call for right and bottom. My right is to increase column by 1. Let's take a variable right, and let's take a variable bottom, and I have to recursively call for this bottom by increasing this row, and at the end I have to return all the total possible ways we can try with this right and bottom. I hope this works. Yes, let's submit this code. And time limit exceeded. Let's think of a better way. Let's take the same example. Suppose my robot is here and I have to reach this finish, right? Can you guys think of a way like, suppose if I want to calculate for this cell, 2 cross 2 column, sorry, this second row and second column, I will do like, I can go in this way or I can go in this way. So I have two possible ways. Can move in this way or this, right? Can I say, guys, if I want to calculate for this cell, this 2 cross 3, sorry, second column and third row. Let's take a table of same size as taken before. Here is my robot and here is the finish. Let's say if I want to calculate for this cell, I know I can only move in one direction, right? And I am reaching here. There is a one way. And if I want to calculate for this cell, I can say the same way I can calculate. I can move right again, and there is only one way. What if I want to say to calculate for this column? I know I can move to bottom and reach here. There is one way, and again if I move to bottom, there is only one way I can reach here. Or I could say like, if my I is equal to 0, for this entire row I have 1, and for this entire column j is equal to 0, I have 1 in every cell. Can you guys think in a way like, if I want to calculate for this cell, can I say I can use this previous row and previous column, and if I add them up, I will get 2. And if you calculate it practically, you know that there is only two way, in this way or this way. And if I want to calculate for this, I have already calculated for the previous previous column and previous row. If I add them up, I will get answer for this cell, and in this way I can calculate for this cell. I have to add this previous row and previous column, and for this last finish I have to calculate this previous row and previous column. I will get 6, right? And this is my answer. Let's write code for this approach. I have to take a DP and it should be of size m cross n, and for my entire row I have for entire row I is equal to 0, I have let's take j because I have to move through columns, and should be n. DP of this let's say for this I is equal to 0 entire row. If I'm moving through j I have to place 1. For this row I have to place 1, and this column I have to place 1 in every cell. Move through n, and for my entire column 0 I have to place 1, and for next cells for this ij index I have to add previous row with the previous column. This is my previous row, and to add with the previous column. And at the end I have to return this last row column. Let's run this code. Okay, place here I. Yes. Yes, it works. Let's talk about time complexity for both the cases. Let's take this recursive case. Let's take a table. Let's take same table, and I know for this z is equal to 0. For this column I can take two decision to go to this right or this bottom, and again like this right or bottom. Let's draw here. This bottom or this right, and for this bottom I again have two choices to go to the bottom or this right, and again for this one I again have two choices to go to this bottom or right. and I know if for this R I'm having the same number of cells. So what I will do, I will, let's take this tree, sorry, and put it under R, and it formed the same tree. Because it have the same number of cells as this in this column. And again, if you want to calculate for this R, it will be same. And if you guys notice one thing, I know like if you calculate this whole for the table, you will notice that for this level I have 2 raised to power 1 instruction. For this I have 2 raised to power 2, and in this way uh, actually let's say for this path I'm uh, like for this I'm having m rows, so it will go till m length, but this tree is not limited to this m only. Like in this path shown here, I'm actually going till this m, but this n also. So like for this somewhere in this branch I'm going till m plus n. So in the worst case you can say like it is somewhere around 2 raised to power m plus n, and this is my height of the tree. This is my time complexity, and space complexity will be big of m plus n, because I'm shown here like I'm taking this m plus n recursive stack, and this is the time complexity big of 2 power m plus n. Let's talk about optimal case. And in the optimal one, I am going to every cell, and I'm taking previous row and previous column, so my time complexity will be big of m into n, because this 2D matrix have m cross n cells. And let's talk about space complexity. This is my time complexity and this is my space complexity big of and I'm taking this 2D matrix, so m plus n, sorry, m into n. This is my space complexity. If you find this video helpful, please like and subscribe. Thank you.